Hi guys, today's topic is large language models. Uh, so in today's session, we will be seeing what large language models is, what prompt engineering is, and we will be seeing in depth of LangChain and what LangChain or RAG is. So LLMs are a category of foundation models trained on immense amounts of data, making them capable of understanding and generating natural language process. Natural language, and other types of contents to perform a wide range of tasks. So LLMs have become a household name thanks to the role they have played in bringing generative AI to the forefront of the public interest, as well as the point on which organizations are focusing to adapt artificial intelligence across numerous business functions and use cases. Outside of the enterprise context, it may seem like LLMs have arrived out of the blue, along with many companies, including IBM, have spent many years implementing LLMs at different levels to enhance their natural language understanding and natural language processing capabilities. So LLMs operates by leveraging deep learning techniques and a vast amount of textual data. These models are typically based on transformer architecture, like the generative pre-trained transformer, which excels at handling sequential data like text input. LLMs consist of multiple layers of neural networks. Each with parameters that can be fine-tuned during training, which are enhanced further by numerous layers known as the attention mechanism, which dials in specific parts of datasets. So during the training process, these models learns to predict the next word in a sentence because on the context provided by the preceding words, the model does this through contributing a probability score to the recurrence of words that have been tokenized, broken down into a smaller sequence of characters. The tokens are then transformed into embeddings, which are numeric representations of this context. To ensure accuracy, this process involves training the LLM on a massive corpus of text in the billions of pages, allowing it to learn grammar, semantics, and conceptual relationship through zero shot or and self-supervised learning. Once trained on training data, LLMs can generate text by autonomously predicting the next word based on the input they have received and drawing on the patterns and knowledge they have acquired. The results is a coherent and contextually relevant language generation that can be enhanced for a wide range of NLU and content generation tasks. Okay, so LLMs can also be trained using reinforcement learning. LLMs also excels in content generation, automatic content creating for blog articles, marketing or sales materials, and other writing tasks. In research and academia, they aid in summarizing and extracting information from vast data sets, accelerating knowledge discovery. LLMs also play a vital role in language translation, breaking down language barriers by providing accurate and contextually relevant translation. They can even be used to write code or translate between programming languages. Okay. So some benefits or most important things that NLM can do is text generation, content summarization, AI assistant, code generation, sentiment analysis, and language translation. Okay, so we will be seeing like most important part. An LLM is transformer. So as we already know, like ChatGPT is making waves worldwide, attracting over 1 million users in record time. As a CTO for starters, I discussed this revolutionary daily due to the persistent buzz and hype surrounding it. The applications of GPT are limitless, but only some take the time to understand how this models works. So GPT generative pre-trained transformer is a type of language model that has gained significant attention in recent years due to its ability to perform various language processing such as text generation, summarization, and question answering. So large language models are trained on massive amounts of text data. As a result, they can generate coherent and fluent text. LLMs perform well on uh, various natural language processing tasks such as language translation, text summarization, conversational agents. Okay. So the transformer architecture is a fundamental building block of all language models with transformers. The transformer architecture was introduced in the paper Attention is All You Need, published in December 2017. The specified version of the transformer architecture looked like this. Okay. There are seven important components in the transformer architecture. So let's go each of the components and understand what they do in a specified manner. The first is the input and input embeddings. The tokens are entered by the user are considered inputs for the machine learning model. However, model only understand numbers, not text. So these inputs need to be converted into a numerical format called input embeddings. Input embeddings represents words as numbers, which machine learning model can then process. These embeddings are like a dictionary that helps the model understanding the meaning of words by placing, placing them in a mathematical space where similar words are located near each other. During training, the model learns how to create this embedding so the similar vector represent words with similar meaning. The next is positional encoding. In natural language processing, the order of words in a sentence is crucial for determining the sentence meaning. However, traditional machine learning models such as neural networks do not inherently understand the order of input. To address this challenge, positional encoding can be used to encode the position of each word. Uh, each word in the input sentence has a set of numbers. These numbers can be fed into a transformer model along with the input embeddings by incorporating positional encoding into the transformer architecture. Then we have a encoder. The encoder is a part of a neural network that processes the input text and generate a series of hidden states that captures the meaning and context of the text. The encoder then GPT first tokenizes the input text into a sequence of tokens, such as individual words or subwords. It then applies a series of self-attention layers, self-attention layers, thinking of its voodoo magic to generate a series of hidden states that represent the input text at different levels of abstraction. So multi-layers of encoder are used in a transformer. Then we have outputs. During training, the decoder learns how to guess the next word by looking at the word before it. To do this, we move the output sequence over one spot to the right. That way, the decoder can only use the previous words. With GPT, we train it on tons of text data, which helps it make sense when it writes. The biggest version, ChatGPT, has 175 billion parameters and was trained on a massive amount of text data. Some text corpora we use to train GPT include the common core web core, the book corpus dataset, and the English Wikipedia. This corpus have billions of words and entities. So GPT has a lot of language data learned from. And then we have output embeddings. Models can only understand numbers, not text, like input embeddings. So the output must be changed to a numerical format known as output embeddings. Output embeddings are similar to input embeddings and go through positional encoding, which helps the model to understand the order of words in a sentence. The loss function is used in machine learning, which measures the difference between a model's prediction and the actual target values. The loss function is particularly important for complex models like ChatGPT language model. The loss function adjusts some parts of the model to improve accuracy by reducing the difference between predictions and targets. The adjustment ultimately improves the model's overall performance, which is great. Then we have a decoder, the positionally encoded input representation and the positionally encoded output embeddings go to the decoder. The decoder is a part of the model that generates the output sequence based on the encoded input sequence. During training, the decoder learns how to guess the next word by looking at the words before it. Okay. Then we have linear layer and softmax. After the decoder produces the outputs embeddings, the linear layer map them to a higher dimensional space. This step is necessary to transform the output embeddings into the original input space. Then we use the softmax function to generate a probability distribution for each output token in the vocabulary, enabling us to generate output tokens with probabilities. Okay, so the concept of attention mechanism, the transformer architecture beats out other ones like RNNs or LSTMs for language processing. The reason for that superior performance is mainly because of the attention mechanism concept that the transformer use. The attention mechanism lets the model focus on different parts of the input sequence when making each output token. The RNN don't bother with an attention mechanism. Instead, they just flow through the input one word at a time. On the other hand, transformers can handle the whole input simultaneously. Handling the entire input sequence all at once means transformers do the job faster and can handle more complicated connections between words in the input sequence. And whereas in LSTM uses a hidden state uh, to remember what happened in the past, still they can struggle to learn them when there are too many layers. Meanwhile, transformer perform better because they can look at all the input and output words simultaneously and figure out how they are related. So they're really good at understanding long-term connections between words. Okay. So next we will be seeing like how LLMs can be used for our own task. Like first we need a problem to solve that. Like if we need a essay to be written or a text to be summarized or the sentence that to be translated, or we need something information to retrieve from a Google, or we can use invoke APIs and actions. So this can be used for it. And then we have something called RAG. So the general purpose of language models can be fine-tuned to achieve several common tasks such as sentiment analysis, name entity recognition. These tasks generally don't require additional background knowledge. For more complex and knowledge intensive tasks, it's possible to build a language model based system that access external knowledge source to complete tasks. This enables from factual contents consistency, improves reliability of a general response or reliability of generated response. So Meta AI research introduced a method called retrieval augment generation to address such knowledge intensive tasks. RAG combines an information retrieval component with a text generator model. RAG can be fine-tuned and its internal knowledge can be modified in an efficient manner and without needing retraining the entire model. RAG takes an input and retrieves a set of relevant or supporting documents given a source. Source example Wikipedia. The documents are concatenated as a context with the original input prompt and fed to the text generator, which produces final output. This makes RAG adaptive for situations where fact could evolve over time. This is very useful as a RAG parameter knowledge static. RAG allows language models to bypass retraining, enabling access to the latest information and generating reliable outputs via retrieval based generation. So when we need to use RAG is when we have a domain specific knowledge or we want assistant in a specific area or where we want to increase the LLM's accuracy, you can use RAG. Or when we have hallucinations in LLMs, we can use RAG by allowing your user to see when the information comes from. Like we want a website where there's a trust, like so we can use RAG at that time. Yeah. So this is the architecture of RAG, where there is a knowledge base, and there is a LLM where a query is given to the LLM, and the LLM uh, gets the data from get the context of from a knowledge base and then given to LLM, and there is a some post processing thing is done, then the response is given. This is a basic architecture of RAG. So the next topic we will be seeing is prompt engineering. So prompt engineering is also very important to improve the LLM's thing. So LLM prompt engineering is a process of so generative artificial intelligence systems are designed to generate specific outputs based on the quality of provided prompts. Prompts Prompt engineering helps generative AI models better comprehend and respond to a wide range of queries, from the sample to the highly technical. Okay. The basic rule is the good prompts equals a good results. Generative AI results on the iterative refinement of different prompt engineering techniques. Uh, Effectively learn from diverse input data and adapt to minimize bias, confusion, and to produce more accurate responses. So generative AI models are built on transformer architecture, which enable them to grasp the insights of language and process vast amounts of data through neural networks. AI prompt engineering helps the models the model output, ensuring the artificial intelligence responds meaningfully and coherently. So the primary benefit of uh, prompt engineering is the ability to achieve optimized outputs with minimal post-generation effort. The prompt engineering involves instructions and the context passed to the language to achieve a desired task. Okay. So here is an example given. Like this is the prompt the sky is. So this is the response given by it. Okay. Basic prompt. We have a different types of prompts, different types of prompts, first short, zero short. Okay. So there is a elements of prompt. The prompt comes from the following components. There is instruction, uh, and the context and input data, and then we have a output indicator. Okay, so here is an example. Instruction means classify the text into the neutral or negative or positive, and the input, we can even explain the instructions like what we have to do. Here the input data is I think the food was okay. Now the output indicator is sentiment. So this is the format that we want the output in. Okay. So we will be seeing this all things like task covering like text generation, question answering, text classification, role playing, code generation, reasoning using prompts. Okay. So if there are, as I said, there are different types of prompts, different types of promptings that we can give, like a zero shot prompting, one shot prompting, and few shot prompting. So zero shot prompting is there is a no example given to the LLMs, and a one shot prompting is an example is provided, and a few short prompting is a few examples, typically 3 to 6 examples are given. Okay. So here it is like we want a summarization, like here we gave a context like a text that we need a summarization, and here we have given an instruction like explain the above one sentence. So it's just process all text and give us the summary. Then we have a question answering. So we have a given first instruction like answer the question based on the context below. Keep the answer short and concise. Response unsure about the answer if not sure about the answer. So here we have given the instruction that it should be following. Then we have a given a context like there is a sentence or there is a para that it's find the answer from. And the question is what was OKT3 originally sourced from. So it searched from the context and give us the answer. So you can select it is a it follows the instruction. Then we have a text classification similar like uh, we are giving instruction like we should be classifying into neutral, negative, or positive. Then we have given a text. Then it give the output like it's a neutral thing. So there are different techniques like few shot prompting, chain of thought prompting, self consistency, knowledge generation prompting, and React. So we will be discussing few like few short prompting. Few short prompts is a like we will be giving a few examples to the a model, and using that examples it generates the prompt. So here we have given like this is the example, the odd number in the group added up the even number in a series, and then we have given the answer, the answer is false. Then we similarly gave the few examples, and at last we have just given a series and give the model, so it answer like this answer is true like that. Okay. Then we have a chain of trans like we are instructing the model more in a reason way. So here we have given us like the instruction like the odd numbers in this groups added up to the even number 4, 8, 9, 15, 12, 1, 1, sorry 2, 1. And then we have given a small reason like how we are doing it. Adding all the odd numbers 9, 15, 1 gives 25. The answer is false like that. So if we give the this example and the instruction or the question we want, the odd numbers in this group added up to the even number 15 to the 15. So it just gives the reason and then it gives the answer. This is a chain of thought, and this is the zero shot prompting. Let's uh, so this involves let's think step by step. Like gives the problem that is given, and it gives a level apple the answer. Now, if I stay, let's think step by step. So you can see the answer is changed to 10 apples. Okay. So here it goes on step by step. Like first you started with 10 apples, you generated, you gave away 2 apples to the neighbor and 2 to the repairman. Do you have a six? You have 6 apples left. Then you bought 5 more apples. So it gives the reasoning like step process. Okay. So this is important. This is today's lecture. So thank you, everyone. If you are new to this channel, please do subscribe and do like the video. Do comment out if you have any doubt. Thank you.